Let's take a simple look at a very, very simple azo dye. And actually this one's probably colorless because where it absorbs. Now, a unique property of azo dyes comes about from the fact that we have these conjugated aromatic systems. So we have two benzene rings connected by a double bond. It basically allows the effects on one electron ring to translate into the other ring. And so we end up getting these gigantic molecular orbitals. Now, a consequence of aromaticity, and it's something that you would have to prove with molecular orbital theory, is that typically the HOMO and the LUMO exist on the aromatic parts of the molecule. So our HOMO and LUMO are basically going to come about from the electrons that are over the entire molecule. Now, we'll talk more in the next video or a subsequent video in how this becomes different when you start doing organometallic dyes. But for aromatic azo dyes, this is kind of what's happening. Typically with aromatic compounds, your HOMOs and LUMOs exist between orbitals within the aromatic system itself. So let's just draw our general HOMO-LUMO. And we're not going to say anything about, because this would be nigh impossible to draw the molecular orbital diagram for without a computer. So given this molecule, we would expect some baseline energy, lambda baseline. As we add electron density to these rings, we add electron donating groups. Well, have you ever thought about why that would work? I'm just kind of curious, because if you really think about it in terms of Lewis theory says that the electrons are really kind of localized between the atoms. So how does electron withdrawing work? This is where molecular orbital theory is going to come in. So let's say we attach some group X to one of the rings and it starts pulling electron density. Well, how does it pull electron density? It's more electronegative. And what that's going to do is it's going to start dropping the energy of our HOMO and raising the energy of our LUMO. And that's why it's electron withdrawing, is that it's so much better at holding onto electrons that more of the electron density is going to move towards it. If we were to draw the shape of the HOMO, it's going to become increasingly more and more biased towards this X molecule. So by adding electron withdrawing groups, what we do is begin to increase that HOMO-LUMO gap, because it's basically more stabilizing, or the electrons are more stabilized because of that more electronegative element. This becomes electron donating. We start moving the two together. So we start going to lower energy. We start looking at things shifting towards the red-orange part of the spectrum versus blue-violet with something like X. Now, there's only so much you can do. Okay, so you can't add, there's nothing more electronegative than fluorine. So once you stick F on there for fluorine, you can't really tune it in more. But we can definitely start throwing in more and more groups. And we can start dialing it in, because something like fluorine is not necessarily as good at electron withdrawing as something like a nitro group or an SO3 group. So we can start dialing in the energy of these HOMO-LUMO gaps by changing the substitutions. Let's say we add two electron withdrawing groups and it's not enough, we add 3 and it's too much, well then we can also add electron donating groups back. So this is the power of azo dyes. We have our base dye, which is pretty easy to synthesize, and we can start functionalizing the benzene rings with electron donating withdrawing groups to tune in that HOMO-LUMO gap and really start triggering in what color we want to get on the spectrum. So how is this different with organometallic compounds? Well, we'll talk about that in the next video.